Example in semi-infinite plate to check the Laplace equation for its solutions. This is a Laplace equation under these two homogeneous boundary condition where the solution is bounded when x tends to infinity. This is open. This is open. This is open region, and u0y is equal to g of y. We solve the Laplace equations using the method of separation of variable uxy is equal to x of x and y of y. Using this function here in this function and using the previous technique, we get a ratio s. Making two differential equation from this ratio, we get the first differential equation with y variable in this under these boundary conditions. Solving this say homogeneous second order boundary equations, lambda n is equal to n square pi square over b square, where the solution become s. In general solutions, x double prime and minus n square pi square b square xn is equal to 0. Solving this differential equation, we get the solution in this form. Since uxy is bounded, so x of x is bounded as x tends to infinity. So n is equal to 0 for all n. N is equal to 0 for all n. So xn of x is equal to e power minus n pi e power minus n pi x over b. Xn, the solutions become s. When x tends to infinity, an is equal to x. When x tends to infinity per bounded solution, it must be that an is equal to 0, because when x tends to infinity, this tends to infinity, but the solution is bounded. Therefore we are forced to put an is equal to 0. From 1a and 3a, we have the series solution as uxy n is equal to 1 up to infinity bn x n of x y n of y, which is equal to putting the value of x n of x y n of x in this series. This is say 4a. Here we use the boundary conditions u0y. Here putting x is equal to 0 in this series solution, we get bn sin n pi y over b, which is equal to g of y. Using the Fourier series coefficient method, orthogonality condition, using the orthogonality condition to calculate bn 2 over b, 0 to b gy sin n pi y b dy. 4a is the required solution with this coefficient of Fourier, the Laplace equation solution. Now in polar form, we are going to discuss the solutions in polar form of Laplace equations. Already, dear student, you have known from complex analysis that if we put x is equal to r cos theta, y is equal to r sin theta in partial square u partial square plus partial square u partial y square is equal to 0. This is a Laplace equation in a rectangular coordinate. If we put these polar coordinate, this equation converted to this form, which is known as a Laplace equation in polar coordinate r of theta. Now consider a circle with radius a in angle theta. Here keep in mind that here the temperature at u0 theta is equal to 0, and here ua theta say f of theta. But keep in mind that the solution at this and this are uniform. U f theta is equal to f of theta, where f is a periodic function with period 2 pi. U r of theta is equal to u r. This is u r of theta, and this f we turns here, we rotate, then this is u r theta plus 2 pi for a belong to for a greater than r. For all theta, this will play role of homogeneous boundary condition. Keep in mind that this condition will play the role of homogeneous boundary condition. To solve this equation 1 in polar coordinate, using the separation variable method, u r of theta, r of r, g of theta in 1. In putting r double prime g plus 1 over r prime g plus 1 over r square r g double prime is equal to 0. Dividing this equation by r g over r square, if we divide this equation, we get r square capital R double prime plus r capital R prime over r plus g double prime over g is equal to 0. Making ratio from this to say this is equal to lambda. Making two differential equation from this and from this, we get solving this is a homogeneous second order differential equation. equations. Solving this differential equation, we get the solution in this form. But keeping in mind that here I have supposed that lambda is equal to alpha square, say alpha square, and I have considered here lambda greater than 0, because we will discuss three cases: for lambda greater than 0, for lambda is equal to 0, and for lambda less than 0. For lambda greater than 0 alpha square, the solution is. If lambda is equal to 0, the solution become s, because cos of 0, solving this under lambda is equal to 0, we get the solution s. If lambda is equal to minus alpha square less than 0, then this solution become s. Now we know that g of theta is equal to g theta plus 2 phi, as g of theta has period 2 pi. If lambda is equal to 0 and b is equal to 0 and lambda is equal to n square, so lambda naught is equal to 0. For lambda is equal to 0, g naught of theta, say this is equal to 1. And lambda n is equal to n square, gn of theta a n cos n theta plus b n sin n theta, where n start 1 from 2, 3 and so on. Now from 3 we have f lambda naught is equal to 0, then the other equation r square r naught double prime plus r naught prime is equal to 0. This is a second order homogeneous differential equation. If we solve this is a simple equation. By solving by characteristic method, we get the required solution as here c naught and d naught are constant. As r of r is continuous, r is equal to 0. This is a continuous because this is differentiable second times. This require that d naught is equal to 0 in 10. So r naught of r is equal to c naught with lambda is equal to lambda n, which is equal to n square. So this is the equation become Euler equation. The previous equation, this equations become the Euler equations, Cauchy-Euler equation. This is a Cauchy-Euler equation of second order. Solving this equations for Rn, we get the solution in this form as given in 12. Let continue continuously at r is equal to 0. Dn when r is equal to 0, dn is equal to 0. So Rn of r is equal to Cn r power n. This is a 13. Now from 10 and 13, we have u r of theta, r n of r, g n of theta. We have found this and this function, putting this and expanding the series. If n is equal to 0, this become a naught by 2 plus n is equal to 1 up to infinity a n cos n theta plus b n sin n theta r n. Now you know that u a of theta is equal to f of theta. This is non-homogeneous boundary conditions. Putting in 14, u a of theta a naught by 2 plus n is equal to 1 up to n a n cos n theta plus b n sin n theta, and putting instead of r is equal to a power n. Using orthogonality condition for comparison with Fourier series, we have a n is equal to 1 over a power n, 1 over a power n, pi 0 to 2 pi f of theta cos n theta d theta, where n start from 0, 1 and so on, and bn start from here. This is a required solutions. This is a required solution in polar form for Laplace equation with these Fourier coefficient. Now this exercise problem I have given you is assignment. Solve using the separation variable method to solve the Laplace equation, and this is in polar form. You can solve using the previous method. Thank you.